Hello, welcome back. So this is part 2 of relating the classical unknotting number to other generalizations and applications to mostly four manifolds. So we mentioned all of those things a little bit in part 1, the definitions, some context, and the theorems that I'm going to be focusing on giving an idea of the proof for in this part of the talk. Again, this is joint work with Samantha Allen, Kanan Inja, Sungwon Kim, and Benjamin Matthias Rupik. So if you were in part 1, you already saw this sequence of generalizations of the unknotting number, but just to recap, on the left, we have our classical unknotting number. So counting the number of crossing changes we need to get to the unknot. And if instead we don't care about getting to the unknot, but just we want to get to some knot whose Alexander polynomial is equal to 1, that's what's called the algebraic unknotting number of our knot. And for these other generalizations of unknotting numbers, so instead of applying crossing changes, we do full twists on any number of strands that we want, null homologous full twists. And more generally, we can do multiple full twists in a given region, trying to get to the unknot. But again, instead, we could just try to get to a knot which has Alexander polynomial 1. And we have these natural inequalities that come from that. So the vertical ones come from the fact that it's easier to get to a knot with Alexander polynomial 1 than the unknot, which is very special. And the top and the bottom come from the fact that if you're allowed to apply any number of full twists in a given region, that certainly encapsulates the case where you're only allowed to do one full twist or one negative full twist. And so what I'm interested in now is, are these inequalities strict? And the vertical ones are actually, it's not such an interesting question. So the point is that if K is not the unknot, the Surgery description number, the untwisting number, those are both at least 1, but there certainly exist knots which are not the unknot, whose Alexander polynomial is 1. So in that case, the algebraic versions would just be 0. So certainly you can get differences in this kind of vertical direction. So the more interesting inequalities are the horizontal ones on top and bottom. I focused a lot on the bottom one in the part 1, and I'm still very interested in it. When we go about showing the bottom inequality, we'll actually also show that the top inequality, both of them are strict. Right. And so the way that this theorem is framed is in trying to distinguish between the Surgery description number and the untwisting number. And the knots that we'll use are these pretzel knots. So we have these kind of 3 twisting regions, 3 twists on the left, 1 twist in the middle, and some arbitrarily large number of twists on the right, but they must be of the form 10n plus 3. These are half twists. And what we were able to show is that the Surgery description number of these knots is 1, and same for the algebraic version of the invariant, while the untwisting number is 2, and that's also the case for the algebraic version of the untwisting number. And I want to highlight this theorem that I already mentioned a couple of times in part 1. We showed there's this tight relationship between the Surgery description number and the untwisting number. The untwisting number can't be larger than 3 times the Surgery description number. which means that if the Surrey description number is 1, say, the untwisting number couldn't be more than 3. So in the examples that we found, ours differ, the Surrey description number and the untwisting number differ by 1. And what this second theorem is saying is that they couldn't differ by more than 2. And so we're kind of close to nailing down what can happen, but there's still this lingering question: does such a knot exist where the untwisting number is exactly equal to 3, but the Surrey description number is 1? Okay. But we're not ready to answer that yet. So we're interested in this family of pretzel knots, and we claimed that the Surrey description number was 1. So we should find this generalized number of full twists that we can apply somewhere in the diagram to get to the unknot. And so where we're going to do that is this blue unknot there, and we're going to apply 2 full twists at once. That's going to give us the second diagram, which you can see simplifies. And in this part of the proof, it doesn't matter what the number of twists were in that last region. We don't care that it has the form 10n plus 3. No matter what it is, this knot is isotopic to the unknot. For the algebraic version of the invariant, we now know it's more than 1. Actually, you can show it's not 0. The Alexander polynomial of these knots, it's not 1 for any of them. And the untwisting number. Well, when we described our Surrey description move, we said we did 2 full twists in this particular region, and you can think of that as doing kind of 2 parallel plus 1 Dane-Surrey moves, or kind of 2 full twists in these kind of parallel regions. So that means the untwisting number is at most 2. And now what we want to show is that it's not 1. So kind of a more general goal would be find a lower bound for this untwisting number that's not also a lower bound for Surrey description number. And that turns out to be hard in general. And we're not really going to do that. What I will point out is that the algebraic untwisting number is certainly a lower bound for the standard untwisting number. And we're now going to focus on showing that this algebraic untwisting number is 2. And I'll just point out that Canaan showed that actually the algebraic untwisting number is equal to the algebraic unknotting number. So algebraically, the difference between allowing yourself to do a full twist on 2 strands versus more strands actually buys you nothing more. You don't get to a knot that algebraically looks like the unknot any faster. So that's maybe somewhat surprising. So what we actually want is something which can obstruct untwisting number 1, or what we'll actually show is that algebraic untwisting number 1 is obstructed in this particular case. And this obstruction is originally due to licorice and was generalized by Brogic-Friedel to the algebraic unknotting situation. And the setup that we need is you need to consider the double branch cover of a knot. This is some 3 manifold constructed from our knot, which has finite first homology. So that'll be important. Whenever we're in this situation, you can define what's called the linking form on first homology. So this is a pairing that gives you a fraction which we consider mod 1. And more specifically, if you kind of want to know the backstory, the 1 cycle A, if I multiply it by n, I'll eventually get something trivial for some n, for large enough n, because my group is finite. And so that means that n times a bounds 2-chain X, and the linking form is defined as the intersection number of this 2-chain with the other one cycle B, and we divide by n to keep track of this n. And the abstraction that we'll use due to Licorice and Brojik-Friedel is that if the algebraic untwisting number is a 1, there's some restriction on this linking form. So they showed that there's a generator in first homology which pairs with itself in this particular way. So here it is again, and how could we use this? If we wanted to use this, we should try to contradict this linking pairing property. We want to show that our knot does not have algebraic untwisting number 1. And I guess the hard part of this theorem is actually just finding the right family of examples where you can get this to run. And so one thing that's useful about this family that we've chosen is that they're actually 2-bridged. So that means the double branch covers a lens space, which is a particularly nice 3-manifold, which we understand well. And moreover, we understand the linking pairing fairly well on it. At least we know what it is on a particular generator. And because it's a lens space, first homology is cyclic. So we know that, in this obstruction of Licorice and Brojik-Friedel, they just say there's some generator which pairs in this particular way. So it's not enough for us to know how mu pairs with itself. We need to know something about any generator. And what's nice about, being in a cyclic group is that any element is actually t times mu for some integer. So we get some relationship between the pairing of kind of any element with itself from knowing the pairing of mu with itself. And in particular, what we notice is that we have a square. We always have a square in the numerator. And to conclude, you can show that plus or minus 2 is never a square mod 40n plus 5. And so there's no way that kind of any generator for the first homology in this particular lens space could have this property. And I'm sorry, I should say that I have some typos on this page. It should be 40n plus 15 everywhere, not 40n plus 5. Okay, so that shows that the algebraic untwisting number is not 1, so it should be 2, and the untwisting number should be 2, while we showed that the Surder description number was 1. Okay, so I want to come back to this theorem one more time and give a hint at the proof. So the idea is we know what the surgery description number of k is. We have some sequence of some number of full twists happening in various regions, and we zoom in on one of these regions. And in this example, we're doing 6 full twists in this region, and we want to say that can be actually described by 3 full twists on different curves, possibly different curves. And the way that we do this is using Kirby calculus. And, if you don't know what that is, it's just a sequence of moves that I can do on these curves that kind of preserves the ambient manifold, so I don't change the knot type when I'm doing any of these moves. And a bit more detailed for those of you that are interested, one thing that's kind of strange is that there's a distinction between whether we're doing an odd number of full twists versus an even number of full twists. For some reason, the Kirby calculus works better if we're doing an odd number of full twists. So in our analysis, we pop off one of these full twists if we have an even number, and then we focus on the case that we have an odd number of full twists and start doing what are called handle slides to change the framings to get to plus or minus 1. So the top one already is plus or minus 1 kind of by construction, and the bottom ones are not, but after some handle sliding, we can guarantee that they are at the expense of probably grabbing more strands. So the picture will always look like this. It's going to be, these two curves that look almost parallel, and one of them is grabbing the strands one more time, and they have opposite signs. So one is a +1 surgery and one will be a -1 surgery. And so we've taken this 1/6, which you can think of as 6 full twists happening at once, and turn them into actually only 3 full twists happening at once, but on much more complicated curves. And again, we don't know if this is the best possible bound that we can get. We've only shown that there exists a knot with surgery description number 1 and untwisting number 2. So, our natural question is there one with untwisting number 3? And I just want to point out that what we used when we were talking about these pretzel knots is not going to work. We looked at the algebraic untwisting number, and it was a lower bound for the untwisting number. But what we showed is that there's also a tight bound between the algebraic version of surgery description number and untwisting number. And it's better than our previous bound. They can't be off by more than a factor of 2. And so if the surgery description number of our knot is 1, then the algebraic untwisting number can't be more than 2. So we could never use this to show that the untwisting number is at least 3. Right. So what might work? I guess if I kind of knew how well this would work, I'd be telling you a result and not a proposed method of studying this, but this could potentially work. So find a knot with surgery description number 1 and show by some method that it's not smoothly H-slice in any of these 4 manifolds. So connect some of CP2 with itself, connect some of CP2 bar with itself, or this mixed case of CP2 with a CP2 bar. And the idea is what's this relationship between these manifolds and the untwisting number. So if the untwisting number was 2, you could show that the knot would be smoothly H-slice in one of these. And so the 3 cases here correspond to, the untwisting being kind of 2 positive full twists in 2 different regions. It could be 2 negative full twists in 2 different regions, or it could be 1 positive and 1 negative. So the kind of 3 cases. And so, if you could show this to be true, you would obstruct the knot from being untwisting number 2. I'll just say that this is maybe even harder than it might appear to be at first, because this knot is going to be topologically H-slice in at least one of these manifolds, because we know that the algebraic untwisting number is at most 2. And we said there's some relationship between the algebraic untwisting number and being topologically H-slice and connect some CP2 and CP2 bars. So depending on the signs of the twist, it's going to be topologically H-slice in one of these 3 examples. And in general, it's difficult to distinguish between things that are topologically sliced but not smoothly sliced. So, in principle, it seems like something like this might work, but in practice, it would be very hard to find such an example and prove that, really satisfies these conditions. So I hope that you enjoyed that and would like to talk to me about any of this. Looking forward to talking to some of you later in the week.